See the first question. The concept of the photoelectric effect describes wave nature of light, particle nature of light, dual nature of light, none of the above. The concept photoelectric effect describes particle nature of light. So option B is correct. See the second question. Einstein was awarded the Nobel Prize for his photoelectric effect, not for the theory of relativity. See the third question. The photoelectric effect is the inverse process of X-ray production. In X-ray production, when the fast-moving electrons are suddenly stopped by a metallic target of high atomic number, X-rays are produced. Whereas in photoelectric effect, X-rays are allowed to fall on a metallic surface, electrons are emanated. The particle nature of light describes photoelectric effect, Compton effect, interference, both A and B. With the help of particle nature, we can explain photoelectric effect and Compton effect. Therefore, option D is correct. Among the following, which one is not an alkali metal? Sodium, potassium, lithium are alkali metal. So, cadmium is not an alkali metal. The photoelectric effect of a material depends on intensity of incident radiation, option B, frequency of incident radiation, option C, potential difference between the electrodes, D, all the above. So all the factors are included. Option D is correct. The minimum anode negative potential at which no photoelectric effect takes place is known as stopping potential. The stopping potential is independent of the intensity of incident radiation. In the photoelectric effect, the saturation current is directly proportional to the potential applied. The minimum frequency of the incident radiation that can cause photoelectric emission is known as threshold frequency. The maximum velocity of the photoelectrons depends upon the frequency of the incident radiation. According to Einstein's explanation, in the photoelectric effect, one electron completely absorbs one photon. The term photoelectric work function denotes the minimum energy used to free the electrons from the metal surface. Which one of the following is Einstein's photoelectric equation? H nu equal to H nu 0 plus half mv square, H nu equal to W 0 plus half mv square, H nu equal to H nu 0, both A and B. This is our Einstein photoelectric equation. Here the work function, photoelectric work function W0 equal to H nu 0. Therefore, option D is correct. Both A and B are correct. Which one of the following is an equation relating to stopping potential? Option A is correct. Say H nu minus H nu 0 is our Einstein photoelectric equation. From this, kinetic energy half mv square equal to H nu minus H nu 0. So in order to stop the kinetic energy, we have to apply potential. E into V0 is actual force acting on this. Therefore, option A is correct. The graph between stopping potential and frequency represents a straight line with the slope h by e. Calculate the velocity of the photoelectron if the work function of the target material is 1.24 electron volt and the wavelength of the incident light is 4.36 into 10 power minus 7 meter. This is 10 power minus 7. 10 power minus 7 meter. This is our photoelectric equation. Then we may write h nu 0 equal to hc by lambda minus h nu 0, because h nu minus h nu 0 is of mv square. Of mv square equal to h nu minus h nu 0. C equal to nu lambda, nu equal to c by lambda. To substitute the values, we can get our velocity 7.43 in 10 power 5 meter per second. If V0 is the stopping potential, then EV0 equal to half mv square. The value of V0 is this much. Heisenberg's sincerity principle is the direct consequence of dual nature of matter. Option C is correct. The uncertainty principle applies to non-commuting canonically conjugate variables. According to the uncertainty principle, delta x into delta p greater than or equal to h cross by 2, delta e into delta t greater than or equal to h cross by 2, delta j delta theta greater than or equal to h cross by 2. All the above is correct. Delta x is uncertainty in position, delta p is uncertainty in momentum, this is uncertainty in energy, the uncertainty in time, delta j is uncertainty in angular momentum, this is angle, uncertainty in angle. The value of the Laplacian operator in Cartesian coordinates is option E, dou square by dou x square plus dou square by dou y square plus dou square by dou z square. The momentum operator is h cross by I into delta. If you multiply numerator and denominator by I, you can get minus I h cross delta. Then h cross into dou by dou t is not our momentum operator, but A and B are correct. So option D is correct. The x component of the momentum operator is h cross by I into delta x minus I h cross dou by dou x, h cross by I into dou by dou x. All the above, all are correct. So option D is correct. The Hamiltonian operator is h equal to t plus v, h equal to half mv square plus v, h equal to p square by 2m plus v, h equal to minus h cross square by 2m del square plus v. All the above. See, all the above is correct because T is our kinetic energy, V is our potential energy. Multiply numerator by m and also the denominator by m, we can get m square v square by 2m. mv is our p, so p square by 2m. You know the momentum operator, p equal to minus I h cross delta. Then p square is equal to minus and minus plus I square minus 1 minus h cross square del square. Here this is not del square, minus I h cross delta, momentum operator. Then p square is minus h cross square del square. So all are correct. Option E is the answer. The Schrodinger time independent wave equation is C del square psi plus 2m by h cross square in t minus c into psi equal to 0. This is correct. But instead of h cross, we may put h by 2 pi. h cross equal to h pi Therefore, h cross square is equal to h square divided by 4 pi square. So option B is also correct. So both A and B are correct. Option C is correct. Schrodinger time independent wave equation for a free particle. A free particle is the one in which no force is acting or a constant force is acting. Therefore, V value equal to 0. Then option B is correct. The energy of a free particle is P square divided by 2m. Then E equal to T plus V. For a free particle, V equal to 0. E equal to half mv square, which is equal to m square v square by 2m. This is p square by 2m. The energy operator is h cross dou by dou t. The time dependent Schrodinger wave equation is minus h cross square by 2m del square plus v into psi, which is equal to h cross dou by dou t into psi. This is our Hamiltonian operator. This is our energy operator. See this is Hamiltonian H. This is our energy operator E. So H psi equal to E psi, provided H and D are Hamiltonian and energy operators. Therefore, option D, both A and B are correct. The relationship that connects the momentum and wave vector is P equal to h cross k. We know that k equal to 2 pi by lambda. According to de Broglie, lambda equal to h by mv. Therefore, k equal to 2 pi by h into mv, which is equal to p. mv is our p. H by 2 pi is h cross. 2 pi by h is 1 by h cross. So p by h cross. Therefore, p equal to h cross k. A wave function is said to be normalized if its norm value is unity. The norm of the wave function is square root of the scalar product of the wave function with itself. So option A is correct. Then if you see the B, that's not correct. See option C, that is also correct, because the meaning of writing psi comma psi, this parenthesis is equal to psi star psi theta. So options A and C are correct. So option D is correct, both A and C. The normalization condition of a wave function is psi star psi theta equal to 1. The orthogonality condition of the two wave functions, option A psi 1 star psi 2 theta equal to 1. Option B psi 1 star psi 2 theta equal to 0. Option C psi 1 star psi 2 star theta equal to 0. Both option B and C are correct. The product of one wave function with the complex conjugate of another one should be vanished. Then the two wave functions are said to be mutually orthogonal. That is a condition. The wave function may be real, complex, real or complex, none of the above. Option C is correct. Say psi equal to A plus IB. The position probability is represented as P of r comma t is psi star psi. P of r comma t is absolute square of psi. Both A and B, P of r comma t is psi in the Brond ket space. These two are correct. Both A and B are correct. So the correct answer is option C. Among the given, which one specifies orthogonality condition of two wave functions? See, this is a repeated question. Both B and C are correct. Among the given, which one specifies the orthonormality condition of the two wave functions? If I equal to J, you may write psi 1 star, psi I star, psi I d tau equal to 1, or psi j star, psi j d tau equal to 1. If I equal to j, delta ij equal to 1. These two are normalization. If I not equal to j, delta ij, Kronecker delta, is equal to 0. Therefore, psi I star, psi j, d tau equal to 0. So, option A is correct. Degeneracy means multiple eigenfunctions having the same energy, different eigenfunctions having different energy, zero energy, none of the above. Degeneracy means multiple eigenfunctions having the same energy. Say this is psi 1 and this is psi 2. Both of them are having the same energy. This is degenerate state. In a particular state, if the probability distribution function is independent of time, that state is known as stationary state. The probability density P of r comma t is psi star psi. In the non-relativistic limit, P of r comma t is psi star psi. The value of the probability current density is J of r comma t equal to IH cross by 2m psi into del psi star minus psi star into del psi. The energy eigenvalue of a particle in a one-dimensional box is, say, n square pi square h cross square divided by 2ml square is the correct answer. If you replace h cross by h pi 2 pi, you may get n square h square divided by 8ml square. So both B and C are correct. So the option D is correct. Here h cross equal to h pi 2 pi. The normalization constant in the particle in the box problem has a value of 2 by L inside the root. The eigenfunction of a particle in a box is psi n equal to 2 by L sin n pi by L into x. Psi n equal to A sin kx. Here A equal to 2 by L, normalization constant, k equal to n pi by L. Therefore, options A and B are correct. So, the correct answer is option C. This is C. For a particle in a box, the ground state wave function is, instead of n, we have to put 1. So psi 1 is equal to 2 by L inside the root sin pi x by L. Option B is correct. According to classical mechanics, the energy value of a particle in a box is from 0 to infinity. In quantum theory, the probability of finding the particle in a box is at its maximum at antinode. The particle in the particle in a box problem, the momentum of a particle is, say, E equal to n square pi square h cross square divided by 2m L square. But for a free particle, energy E equal to p square divided by 2m. That's p square by 2m is equal to this quantity n square pi square h cross square divided by 2m L square. Therefore, p square equal to n square pi square h cross square by L square. Then p equal to n pi h cross by L. N pi h cross by L. So option B is correct. Then if you replace h cross by h by 2 pi, n pi h by 2 pi L. Therefore, p equal to nh by 2L. Option C is also correct. Therefore, the correct answer is both B and C. Option D is correct. The wavelength of the de Broglie wave associated with a particle in a box in the first excited state is equal to the length of the box. You know that momentum P equal to nh by 2L. For the first excited state, the value of n equal to 2. P equal to 2h by 2L. H by L. You know that lambda equal to h by P. H divided by h into L. Therefore, lambda equal to L. So, option C equal to the length of the box is the correct answer. A node is a position of minimum or zero displacement. Say nodes are located at x equal to 0, L by n, 2L by n, NL by n. When n equal to 1, nodes occur at x equal to 0 and x equal to L if you put n equal to 1. When n equal to 2, nodes occurs at x equal to 0, x equal to L by 2 and x equal to L. When n equal to 3, nodes occur at x equal to 0, L by 3, 2L by 3 and x equal to L. The antinodes are located at x equal to L by 2n, 3L by 2n, 2n minus 1 divided by 2n into L. When n equal to 1, antinodes occur at x equal to L by 2. When n equal to 2, antinodes occur at x equal to L by 4, 3L by 4. For the nth quantum state, there are n antinodes. That is, there are n equal probable position in the box at which the particle is most likely to be found. Similarly, there are n minus 1 nodes, each node lying in between two antinodes. That is, there are n minus 1 equally spaced positions where the probability of finding the particle is 0. The two positions x equal to 0 and x equal to L are permanent positions of the nodes. The energy eigenvalue of a particle in a three-dimensional box is pi square h cross square divided by 2m nx square by lx square plus ny square by ly square plus nz square by lz square. The energy eigenfunction of a particle in three-dimensional box is, say, 8 divided by Lx Ly Lz inside root sin pi x by Lx sin pi y by Ly sin pi z divided by Lz. This is correct. Here Lx Ly Lz are replaced by volume. So option B is also correct. Both A and B are correct. So option D is correct. The normalization constant of a particle in three-dimensional box is root of 8 divided by Lx Ly Lz Then instead of Lx, Ly, Lz, we can put V. So A and B are correct. Therefore, option D is correct. The normalization constant of a particle in three-dimensional cubical box is 8 divided by L cube inside the root. The momentum value of a particle in a three-dimensional cubical box is pi h cross by L in x square plus m x plus n square power 1 by 2. In a particle in a box problem, the potential energy of a particle is related to the boundary condition V equal to 0 for x greater than or equal to 0, less than or equal to L, and V equal to infinity for x less than 0 and greater than L. Which means that when the particle is outside the box, the potential is infinity. If the particle is present inside the box, the potential is 0. So option A is correct. But as far as our potential barrier is concerned, this is entirely changed. You should know the difference between potential step and the potential barrier. A potential step corresponds to the force field acting on a particle being 0 everywhere except in a limited region. Potential barrier has a double step. First step from V of x equal to 0 to V of x equal to V0, and the second step from V of x equal to V0 to V of x equal to 0. So here there is a condition V of x equal to 0 for x less than 0, V of x equal to V0 for x greater than or equal to 0, less than or equal to A. V of x equal to 0 for x greater than A. If the energy of the particle is greater than the barrier, the momentum of the particle is 2me inside the root. If the energy of the particle is greater than the barrier, the momentum of the particle in the second region is 2m into E minus V0. The formula for reflection coefficient is reflected probability current density divided by incident probability current density. The reflection coefficient for a particle with energy greater than the barrier width is option A. The transmission coefficient for a particle with energy greater than the width of the barrier is option A. The depth of penetration of a particle of mass m and energy E less than V0 is h cross divided by 2m into V0 minus E inside the root. A proton and a neutron having the same energy penetrate a given rectangular barrier. Which particle has a greater depth of penetration? Proton has greater depth of penetration because the depth of penetration is given by the formula h cross divided by 2m into V0 minus C inside the root. Here the mass of the neutron is greater than the mass of the proton. Therefore, proton has higher depth of penetration. The relation between the coefficient of reflection R and transmission T for a particle incident on a potential step with energy greater than the height of the barrier is R plus T is equal to 1. The Compton shift is given by the formula d lambda equal to h divided by m0 c into 1 minus cos theta. Here m0 is rest mass of electron, c velocity of light, theta angle of scattering, h our Planck's constant. The Compton effect can be observed with X-rays because the wavelength of X-rays are lying between 1 to 100 Armstrong unit, but UV and visible radiations are having higher wavelengths, so that we won't get our Compton effect with the help of these two. Only with the help of X-rays we can get. The Compton scattering depends upon only the angle of scattering, which is independent of nature of the material, wavelength of the incident radiation. When the incident radiation of wavelength lambda is scattered through an angle theta by an electron, the scattered wavelength of X-rays is greater than that of the incident radiation by an amount 0.0242 is nothing but our H divided by M0C value into 1 minus cos theta Armstrong unit. Option A is correct. When the angle of scattering is 90 degrees, that is theta equal to 90 degree, what is the value of Compton shift? D lambda equal to H divided by M0C into 1 minus cos 90 degree in this case. Say this is 0, cos 90 is 0, which is equal to H divided by M0 into C. Say option A is correct. Then option B is also correct because H divided by M0C value is 0.0242 Armstrong unit. Therefore, option C, both A and B are correct. When the angle of scattering is 180 degrees, that is 180 degrees, the Compton shift is what? Cos 180 is minus 1, so 2H divided by M0 into C. In this formula, put cos 180 is minus 1, so 1 minus of minus 1 is plus 2, so 2H divided by M0C is our Compton shift. The value of Compton wavelength is option A, H divided by M0C. The value of Compton shift is 0 when the angle of scattering is the value of Compton shift d lambda is 0. Say d lambda equal to H divided by M0C into 1 minus cos theta. If you put theta equal to 0 degree, cos 0 1, 1 minus 1 0. So d lambda equal to 0. Option D is correct. Cos 0 1. The properties of wave functions include the wave function must be single valued. That means for the given values of x, y and z, psi is having only one value. The wave function should be continuous and the derivatives are also continuous. The wave function may be real or complex, but the position probability is always real. If you say psi equal to a plus ib, then psi star equal to a minus ib. Then psi star psi is our absolute square of psi, is a real quantity. So all the above are correct. The position probability is always a real quantity. The maximum velocity of the photoelectron is 2eV0 by m because of mv square is equal to e into v0. V equal to 2e v0 divided by m v square equal to m. Then v equal to 2e v0 divided by m inside the root. When the photoelectric effect is taking place, increasing the intensity of light will increase the number of electrons released. The kinetic energy of the emitted photoelectron is h into nu minus nu 0 because photoelectric equation is h nu equal to h nu 0 plus half mv square. And half mv square kinetic energy equal to h nu minus h nu 0. This is equal to h into nu minus nu 0. The work function of the photoelectric current is different for different metals. The conversion of light energy into electrical energy is achieved in a photo cell. The distance traveled by a photon in a metal before complete absorption is 10 power minus 8 meter. The photoelectric threshold wavelength for potassium is here. They have given the work function as 2 electron volt, 620 nanometer. W equal to hc by lambda 0, lambda 0 equal to hc by w. If you put the value, you can get 620 nanometer. What is the stopping potential when a metal with work function of 0.6 electron volt is illuminated with a light of 2 electron volt? Say h nu minus h nu 0 equal to EV0. Therefore, V0 equal to h nu minus h nu 0 by E. Just h nu incident light energy is 2 electron volt. Then the work function h nu 0 is 0.6 electron volt. If you subtract, we can get 1.4 electron volt. The charge of electron 1.6 is 10 power minus 19. If you convert this electron volt in terms of volt, 1.6 10 power minus 19 is cancelled out. Therefore, we may get 1.4 volt. Option D is correct. The response of the photon of wavelength lambda is 0. The momentum of the photon is h nu by c. You know that E equal to h nu, then E equal to mc square, which is mc into c. Mass into velocity is our momentum, is pc. pc equal to h nu, because both of them are energy. Then P equal to h nu by c. So option B is correct. The number of photons required to give a definite energy W varies inversely as the frequency, because W equal to NH nu, N equal to W by H nu. Therefore, number of photons is inversely proportional to frequency. When a inert gas is filled in the place of vacuum in a photocell, then photoelectric current is increased. By increasing the frequency of incident light, work function will remain constant.